Thank you for coming. So last week, my partner Candace was telling me that I needed to get a haircut. She said, your hair's starting to do that thing where it kind of turns into a bowl. And you know, you're on television, you're wearing that brown jacket that you wear, and you're starting to look a bit ragged, so you got to go get a haircut. So yesterday, finally, I had time to go get a haircut. So I went into the haircut place, booked for 11 o'clock. And I went into the haircut place and got talking to them. They said, what do you do? You know, your standard barbershop type talk. And I said, oh, I'm an earthquake geologist. Oh! Okay, so you're having the time of your life. Yes, but you know, there are personal challenges, but okay. You know the drill. She said, you know, we had a geologist in here last week, a guy named Stefan Winkler from the department as well. And we were asking him about the earthquake. We were having a chat to him, and he was telling us, oh, you know, we're going to get aftershock. We're going to continue to get some aftershocks. That's just sort of a normal thing, and you know how we say that. And then Stefan walked out. He got his hair cut. He walked out. And 5 minutes later, there was an earthquake, a big earthquake. And I said, oh, wow, that's really interesting. So, okay. So we finished my haircut, and I got up, and I walked out, and I was sort of walking across the campus in the university, and all of a sudden I started hearing ding, 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 and the lamps, the light posts were sort of wobbling back and forth, and I thought, oh, that was a decent bit of a shake. And then I went up into the geology department. Of course, all my colleagues were sort of clustered in the hallways and talking to each other. Well, that was a big earthquake stuff, and I didn't really think, I didn't feel it, so I was sort of like, oh, man. So I got on GeoNet, like you all do, and checked the magnitude. And it was a 5.0 aftershock, which is a big aftershock. It was close, it was shallow. So I thought, wow. So the reason I wanted to start with that, of course, is that if you have any geologist friends who have haircutting appointments that you know about, then you can be almost certain that 5 minutes after they're done their haircut, there's going to be a large aftershock. So just keep that in mind. Anyway, thank you for coming. I think I want to start with some sort of broad statements. These may be simple to some, but they are important statements. And I think, you know, the scientific community has done a great job doing the best they can to put a lot of effort in and get a lot of concise and clear information out there, but it has been a challenge, and so I thought we should start at a level playing field. So here we go. Statement number one is that science does not move at the pace of the media, except possibly GeoNet. And we know that because we can get on GeoNet, 20 minutes after the earthquake and find out data. But science is a long-term process, and one of the important things to realize is that science are not omniscient. They don't always agree, and they quite often argue vigorously. They propose hypotheses, they get in big arguments with one another, they test these hypotheses, they write up something, they send it to peer review, and they get reviews back telling them that their ideas were crap and they should revise them, and on we go. And so I think, I'm not going to give you any 100% sure answers tonight, but I'm going to give you a lot of, what I hope to do is give you a lot of knowledge about the processes that are operating, and so you can better understand the nature of these processes. Every major earthquake that we have writes its own story. And so we can use past earthquakes to provide us with useful information about what to expect. But of course, every earthquake is a little bit different. And that's why we will never say with 100% certainty the big aftershocks are done, or we are going to have them for X amount of days. And no one can predict the exact date or time of earthquakes. Not even Moon Man. But we can estimate probabilities based on our past knowledge of earthquakes. And that's something that the Active Tectonics program at the University of Canterbury is doing for 20 years and will continue to do. If we can understand past behavior of faults and timings of earthquakes, we can get some idea about probabilities of future earthquakes. Okay? And finally, one more statement. Earthquakes don't know what time it is. Big aftershocks don't just come on Mondays because they don't know when to come. They just come when they go. They don't keep on schedule. Faults don't keep on schedule. And they don't have street addresses. So when you look up on GeoNet and you say, oh my God, that epicenter was right underneath my house, it's a zone of rock which is deforming quite rapidly and creating that energy. And the locations that you see are plus or minus 5K usually. So you're just getting a general idea. Okay? Hopefully that clears up a few things. But we need to start, obviously, with the aftershock, because I think this was, for a lot of us, not really so much me, but for a lot of people who were indoors or lying down or these sorts of things, quite a major aftershock. It was a 5.0, magnitude 5.0. We've had 12 or so of those around that magnitude, so it wasn't anything particularly special, except that it was about 10 kilometers to the southwest of Christchurch, which means it was close to us. It had a 9-kilometer focal depth, and you'll say, a lot of people will say, oh, the earthquake was really shallow, and that's why we got that energy. But of course, you guys went on GeoNet, didn't you? And you saw it was 9 kilometers. You thought, well, that's not that shallow, really, because the main quake was 10K. So what gives? But I think something that hasn't really been made a lot out of is this centroid depth. It's sort of a cool word, which basically, I'm going to explain to you what that means. But that centroid depth was 4 kilometers. And the epicenter, of course, was near Taitapu, and we experienced quite a bit of damage in that area and other areas. We need to learn a little bit of seismoterminology before we get going with this. The first is what is an aftershock? People ask me that all the time. Email, was that earthquake we just had, was that something different? No, that's an aftershock, right? Because the aftershock terminology is fairly simple. Any earthquake with a smaller recorded magnitude than the main shock in the region surrounding the surface rupture, so we're talking about, if the fault is 40 kilometers long, then we're talking about distances of sort of 80 kilometers around that area, plus or minus a bunch, is an aftershock. It can be on the same fault as the main shock. It can be on other major faults, and they can be on small, little faults, the size of this desk or the size of this room, small things. These aftershocks are caused by changes in the stress state of the crust due to the main earthquake, and after you've had that big earthquake, the relaxation of the crust. They also can form because of changes in pore fluids, so as you squeeze the crust and release it during the earthquake, it's almost like squeezing a sponge. Water gets squeezed into some places and out of others, and so you can trigger earthquakes that way. Changes in the shape of the crust looks entirely different now, and I'm going to show you some pretty amazing images of how different it actually is prior to the way it looked before the earthquake. And also the effect of seismic waves on fault zones. So even faults such as the Alpine Fault experienced a very, very slight and quite possibly insignificant increase in microseismicity. It has nothing to do with a change of volume. It does not mean there's going to be a big earthquake on that fault, but these things tend to happen as you have seismic waves passing through rock masses. And we know these seismic waves travel around the world. They were recording them in the US as well. So those are some important points. The frequency of aftershocks decays rapidly with time. You've heard some scientists talk something about Amori's law, but the timing, the location, the depth, the magnitude, and the type of the earthquake, pretty much everything, cannot be predicted for individual events. Okay? An important point. We can get some idea. I'm going to show you how to do this yourself. You can get some ideas about where you think this should be, but we cannot predict the exact nature of these events. And finally, aftershocks can feel as bad or even worse than the main shock, depending on the proximity of the site to the earthquake. The closer it is, the more we feel it. The type of the earthquake and the rupture process itself, the ground conditions, hard rock versus alluvium, and a variety of other parameters. However, the energy release from this earthquake and the duration of shaking, importantly, is less than that of the main shock. So some people said, boy, that one we had yesterday was horrible. That was worse than the main shock. It might have felt quite bad to a lot of people, but of course the duration of shaking, which is a very important parameter in terms of what gets damaged and what doesn't, was significantly shorter, and I'm sure all of you would agree with that. Okay. So we're blessed to live in New Zealand. Because every time we can look out at the university, we can see these beautiful white snowy mountains. And of course, without earthquakes, we wouldn't have any mountains here. It would be flat and boring like it is in Australia. Just kidding, I like Australia too. But prior to this earthquake, of course, I mean, we're not in an entirely unique situation. We had big swarms of earthquakes and aftershocks in the last 10 years. Is that 10 years? Yeah. In Arthur's Pass area and in the Cass area, okay? Clusters of aftershocks related to big earthquakes and then the gradual settling down of that crust, okay? This is not a new story. This is not a unique story. But like I said, it's a different story. That's what it looks like now, okay? So the difference in that scenario is actually quite intense, and we've had thousands of aftershocks since that main event as the crust is settling down. We can learn a lot from these aftershocks. One more thing we need to talk about before we get going, that's what I mentioned, was this centroid depth. And this is really quite an important parameter. I think you're all going to be thinking a little bit more about this once I explain it. So this is basically a fault rupture plane. Okay? Remember that faults are planes, and when they break along that plane. Now, these arrows here are just modeled slip directions, and the amount of slip in centimeters here that occurs during an earthquake on this fault plane. Okay? Turns out this is one of our models for the Greendale Fault, but this could be any fault in the world. Now, we constantly go on GeoNet and we get reported this focal depth, the birthplace of earthquakes, where they initiate. Okay? So where that rupture actually began. However, the focal depth and what we call the centroid depth are not always in the same place. I mean, quite often they're not. And a lot of times that centroid depth is actually shallower than that focal depth itself. Of course, the centroid depth is the area that has the biggest amount of slip, and that's what has the biggest amount of energy release, which therefore causes that intensity of that earthquake. Okay, so that's an important point to remember. Of course, we know what the epicenter is. The epicenter is the place on the Earth's surface directly above the focal depth. So the area of maximum energy release may in fact be quite a bit shallower than the rupture birthplace. In this case, that recent aftershock we had, the centroid depth was only 4 kilometers. And so that might explain some of your observations when you thought, well, that was a really scary earthquake, but it was 10 kilometers depth. In fact, you might have had an energy release quite a bit shallower, which created that amount of shaking. Also, this might mess up your GeoNet earthquake calibration. You know that game you play with the, that was 10 kilometers depth, 25 kilometers southwest of Darfield. Okay, but that said, that aftershock did actually create quite a bit of ground shaking. So this is gravity, stands for gravity here, and these numbers are basically a percentage of gravity, okay? So 0.2 is 20% of gravity in terms of the acceleration that the ground felt during the earthquake. All right? So here are a bunch of stations. These are accelerometer stations, which basically record how the ground accelerates during the earthquake. We're all our own accelerometers in a way, I suppose. But during that main shock, we had that 7.1 main shock, we had 0.2 to 0.3 Gs in the city, and we had significantly higher Gs in places 1 G and even higher during that main shock, okay? Which is pretty intense shaking. This last one, this 5.0, we had up to 0.28 G, so almost 3 G in Riccarton. All right, so the ground acceleration was almost as intense as that first main event. However, there are a variety of things that are important during an earthquake. The intensity of the ground motion, which we'll be talking about, things like the ground acceleration, and also the amplitude, how fast things go and how broad things go back and forth, sort of the amplitude of these waves. This relates to a variety of things, magnitude, distance, geological properties. The duration is really important as well. And a lot of this was made in terms of when we had that second really big aftershock in Littleton. You know, there was more damage done to buildings that had already been damaged in the first earthquake because you had broken things up and then they got loosened a little bit more. It's like having a longer main earthquake. That relates on a variety of things as well, the earthquake magnitude, the rupture process, etc. And then there's something called frequency content, or the predominant period. And I'm going to show you an example of that. And that's actually really a quite important parameter. It's a difficult thing to quantify, But during an earthquake, when the seismic waves come out, they have different frequencies. And for that reason, they affect buildings in different ways. So you might, for instance, be in a small building and feel like, wow, that was a really major shake. And your mates in the tall building said, oh, I didn't really feel that too much. And things can go the opposite way in there. Okay, so I just want to show you something. This is one of my favorite things. This is an earthquake table for demonstrating what happens to buildings during earthquakes. It's quite colorful and it's a really neat thing. Okay, so I'm going to show you two different earthquakes. Okay, I'm going to show you a high frequency, short period earthquake, and then I'm going to show you a low frequency, long period earthquake. These are buildings. So this is one of the crappy student flats here, and this is like a 2-story nice Maryvale place. This is one of those places on Carlton Mill Drive, maybe. This is one of the places in the city, one of the big ones, okay? Now, this is obviously very simplified because all these buildings are made out of the exact same material in the exact same way, and of course, that's not exactly how life works. And the engineers would be very happy to tell us about that. However, when we have, say, a high-frequency earthquake, we tend to feel the shaking in different buildings. So I'm going to have a high-frequency earthquake. You can see, look at the top buildings. I mean, if you're living in a not so nice house that's quite maybe a 1-story house, then your house probably would have been pretty hardly hit by that one. Okay, so let's go now into a different frequency earthquake. And of course, you wouldn't want to be up there necessarily. These people might have been like, oh, that wasn't too bad. So obviously, frequency content matters as well. And as you can imagine, if I just kept doing this, and I've tried this, I just keep doing this, eventually these things break. That's why I don't have wooden ones anymore. These are metal ones. So obviously, the duration matters. And of course, if I really start cranking on them, the amplitude, that's changing the amplitude. That matters quite a bit too. I better put this down now before I break it, but you get the idea. Okay. So that explains why you might feel things different. So in general, these smaller, closer earthquakes tend to have a shorter period and a shorter duration. The actual amplitude is not always, that depends sort of on where you are, the type of earthquake, these sort of things. But these plots here basically show the change in period as a function of distance and as a function of magnitude. The main thing I want you to get out of this is that the closer you are to the earthquake, the shorter the period. So that's your rapid shaking, right? And the lesser the magnitude, the lower the period. And so close, smallish earthquakes tend to, not always, but tend to amplify shaking more in your smaller buildings. And big, far away earthquakes tend to influence your higher apartments. So one analogy would be, say, comparing an alpine fault potential earthquake with one like we just had. The effects could be quite different. Okay? All right. Now, I gotta admit, I'm a little bit bored with the game that you play with, the guessing the magnitude and all that sort of stuff, because I think we're kind of calibrated okay. And I want to introduce a new game. This is a really fun game if you have kids, because you can actually, there's a lot of power in this game. So when we have an aftershock like that one, the seismologists give us this. This is what they give us. It looks like a beach ball, and they say, here you go. Interpret this. And then there's a lot of power in these, but of course we need to know how to use them first. So these, I want to quickly give you a tutorial on how to use these things. And I created this tutorial at about 4 o'clock in the morning a couple days ago. And I don't know if the coffee beans are trying to tell me something, but imagine a bowl of coffee beans, okay, just sitting on the table, and there's a bunch of seismometers all set up around this bowl of coffee beans, and there's about to be an earthquake, okay? And these two things here are potential faults that are going to rupture during the earthquake. So we have the earthquake, it sends out the waves, and based on the first arrival of P waves at all these different seismometers, the seismologists were able to say, well, that one felt a pull, and that one felt a push, and that one didn't feel anything, and that one felt a pull. And they're able to sort of get some idea as to whether the rocks were pulled or pushed. And it's the same as this bowl of coffee beans. So here are two potential faults going down into the crust, one going north-south, one going east-west. If all we get is that, of course, we don't know whether these coffee beans came from here and these coffee beans came from there, in which case we have a north-south striking fault where we had this block move like that and this one move like that, or alternatively, whether these beans came from here and these ones came from here. But we still have that graphic that helps us understand. So this area felt a push, and this area felt a push. And these ones felt a pull, but we don't exactly know how that pull. It's 90 degrees off, okay? I'm going to show you some of these in a second, so hopefully you're paying attention because there's a test. There's a test coming up. Okay, well, and you can play this all. There's all sorts of different geometries. Of course, those are strike-slip faults moving side on, side on. But there are other ones like this. So, for instance, these beans here have either come from this area or this area. So if they've come from this area, then the beans that were here got blasted out of the cup, and these ones here got pushed down. And there's only one fault that can be used to understand that, and that's this fault here. Okay? So that block moved up, this block moved down. And that's where those beans come from. We can't see the rest of them. Of course, it's equally possible that these beans got blasted out of the cup, these ones moved down, and that's the fault plane. I'm just trying this out to see if it works, and if it does, I'm going to try it with my first years next year. And of course, you know, there are other options like this. So you have beans on the outside. This area is being pulled apart, and the beans in here have either come from above down into there, in which case this is the fault plane, or these beans have come from here and come up to the side of the bowl, in which case that's the fault plane. Now these solutions tell us about whether the crust was pushed together, pulled apart, or slid side on, side on. Okay? There's a test coming. All right, so this is the graphic from that aftershock. And again, there are two possible solutions. But when we get something like that, we're able to look at that data on GeoNet, and we're able to look at orientations of faults in the area, known faults. Keep in mind that the Earth is riddled with faults. And these faults, after big earthquakes, tend to jostle around a little bit. Okay? So the take-home message from this is that there are northeast striking old faults that go through the Porthills, that this earthquake probably related to a right lateral movement on one of these faults, which is what the geology tells us as well. It was probably slip on the order of a few centimeters or something like this, based on this location, but that these are different faults from that main Greendale fault that ruptured, but that this doesn't mean that those faults are going to have massive earthquakes. It just means that they are acting to try to alleviate that change in volume, that change in shape related to that big earthquake. Okay? So that's just an example of how this data can be used. All right, now here's the game. This can be, I know you guys are experts in GeoNet, so this actual plot can be taken directly from GeoNet. And I want you to look at the patterns there and think about the coffee beans moving around and look at all these. These are all aftershocks plotted against location. So there's our beautiful Greendale fault there, and there is one of the mechanisms proposed. There are other mechanisms proposed on a thrust at depth. We're not going to talk so much about that one, but what we can see on the ground is this sort of movement. Now, if you were going to choose one of those fault planes, the one that goes north-south or the one that goes east-west, which one would you choose? Probably the one that goes east-west, probably the one where the coffee beans got moved out of there to there and there to there. Okay? However, there's a whole bunch of mechanisms all around, and you'll notice a lot of them are different. There are ones out here, out in the west, in Hororata, where people felt a very different sort of history than we felt here in Christchurch from that earthquake. Those areas out there tell us that the earthquakes are primarily pushing things together, squeezing things together, and the orientation of the fault is northwest. We look down in this area here, this big belt of aftershocks we have down here, And we've got a whole series of things which are very difficult to interpret, but they are a mixture of side-on earthquakes, quite possibly related to little faults moving dextrally, and then some faults where the Earth is actually being pulled apart. Okay? So this data provides us with a wealth. Now the game is, of course, once you know where the earthquake is from GeoNet, you can guess whether it was a fault which related to the Earth being pulled apart, or being side-on, or being pushed together. Now you might not find this game terribly fun, but some of you might. And so the point is that this actually teaches you a bit more about process as opposed to just guessing. So it's an interesting thing. Those are the aftershocks from 3rd to 6th, and here are the other ones that we've had. A whole mixture of very interesting aftershocks. There's the Littleton event. There's the Littleton event. What sort of earthquake was that likely to be? Well, we think that was probably another one of these side-on earthquakes, these strike-slip earthquakes, where we had what we call right lateral movement. But of course, we can't tell exactly at this stage. Okay, let's talk some more about aftershocks. Everyone wants to know how long, how big. These are difficult questions, all right? But one thing we can do is look at past earthquakes for these sort of records. Let's look at Haiti. January 2010, I think the 12th of January, Haiti had a magnitude 7 earthquake. Similar sort of magnitude that we had. Somewhat smaller, but similar. Okay, that was 9 months ago. The largest aftershock they got was a 5.9. There were no 5s after 1 month, so we got them beat there. They are still getting occasional low 4s. We feel low 4s. So the message there is that 9 months from now, it would be entirely reasonable that every now and then, maybe a couple times a month, we're going to get a magnitude 4 earthquake that we'll feel. And the stomach will do that little thing that it does, a little weird thing it does, and then everything will be fine, right? Baja Mexicali earthquake. One of my colleagues is actually in the exact same position. One of my best mates is in the exact same position as me. A big earthquake happened in his backyard. And he's been working, for a year and a half or something like that before this earthquake and since on this earthquake. Anyway, 7.2 event, the largest aftershock they got was a 5.7. They are still getting a few 4s a month, and this month they got a 5. Okay? Similar magnitude event. Both of these are strike-slip faults, so the same sort of movement. Might give us some idea. If we look at some of New Zealand's historical earthquakes, average aftershocks are 1.3 points lower than the main shock. But of course, there's a lot of variability here. That's why we can't say, that's why everyone was freaking out about this. Oh, we're waiting for the 6.1. The 6.1's coming. We're going to get a 6.1 or a 6 or whatever. We might. But we very equally might not. And I guess when you look at this data, I mean, this is the sort of things that you need to perhaps alleviate your own fears. There's no guarantee. There's a high probability we've had our biggest aftershock. However, there's also a possibility that we will get another bigger one. Okay? But that's just the way it is. There's quite a bit of variability in these. 0.6 to 1.8 smaller than the main shock. But what we do know is that the frequency of aftershocks declines with time for earthquakes. These are some Turkey earthquakes, and it gives these sort of examples. So this is a 7.4 earthquake. The biggest aftershocks they got were sort of between 5.5 and 6, 5.7 or something like that. And of course, hardly any of those events, very few of those events compared to the bigger events. Same with this, these are two Turkey events. This is a 7.2 event. So this shows the distribution. You have lots of small earthquakes and few big earthquakes in terms of aftershocks. And also that after tens to hundreds of days, the number of earthquakes per day, this is with a minimum of 3.4. So these are earthquakes of 3.4 magnitude or bigger, declines quite steadily. Okay? There's going to be bumps on the radar. These things move up and down. But in general, with time, you get a decline in the number of aftershocks. All right? This shows that example again. Now, we can't just take these directly and input them into our scenario because, like I said, every earthquake is different. However, this gives you meaningful data to draw your own conclusions. And in general, when you look at the aftershock data from our earthquake, I like that, our earthquake, you can see that the number of earthquakes per day has definitely decreased. I mean, unquestionably decreased since the since the week following the main earthquake. And the magnitude, the average magnitude, has not. We are getting less frequent earthquakes, but we are still getting decent-sized aftershocks. And with time, those will decrease and become less and less frequent. Okay? All right. I want to go quickly through what I call rock and roll, which is a little bit about my day on the day of the earthquake. Tell you a little bit about the rupture process, and then talk a little bit about something that a lot of you have been thinking about, and that is the Alpine Fault. Should we evacuate New Zealand, the South Island, all move to the North Island? We should all move to Wellington. Okay, so we were asleep, like most of you, during the morning of the earthquake, and of course our house, like your house, began to rattle back and forth, and my partner said, "Is it an earthquake?" And I was like, "Alpine Fault, Alpine Fault." And then I was like, "Oh, maybe Porter's Pass Fault or some other fault." And I was quite excited. And then I went out onto my deck and I looked out, and this was what had happened. The water had surged up, and it was my veggie garden wasn't that flash anyways. But the water had spilled up over the top. Water was coming into the heat pump and all this stuff. I saw it. So I thought, wow, it's pretty amazing. And then I went to my front yard, and there were these sand volcanoes coming out of the ground. There's still lots of water. You all know where I live, right? Yeah, I'm not going to say it. So all the sand volcanoes coming out and things like that. And of course, we walked out onto the street, and we could see power poles that had sunk into the ground, beginning to tilt. This was, like I said, half an hour after the earthquake. And we saw some of the lads coming home from the big night out, not terribly fazed by the event. I don't know if any of you guys know these guys, but I reckon they owe me a beer because they got a lot of publicity out of this. This was on Stuff, this picture. Anyway, it's actually quite a challenge to get boy racer cars over these cracks. So we were sort of like to the city council, you can leave those a little bit, that's all right. Anyway, so immediately after that earthquake, we go look around. My phone was ringing. Candace and I were on NBC in the US about an hour and a half or 2 hours after the earthquake on Skype. We were in, the Associated Press was calling me. I was on the radio, but then I was also trying to do some science and take some photographs and try and document damage. So we went around and we looked at some damage in our area. We saw some damage in the central city. I'm sure a lot of you saw that. At one stage, this particular guy, we didn't have power in our house, so he called my phone and was like, "You can come over and use our power, use our internet, and do the interview and stuff like that." So this was really great that he came to our aid. But this is in our neighborhood as well. And of course, I was on TV One a few hours after that, discussing what I'd seen in the earthquake. Meanwhile, the research team, the University of Canterbury research team, found the active fault scarp by 9:30. Using a mixture of farmer reports and using what the early epicenter location was, driving around, they found the fault. GNS had mobilized crews, and they were in the air, flying around the fault, surveying damage. I finally got to see the fault at 11 o'clock in the morning. It was painful to have to wait that long, but my phone just kept ringing, and then I ended up back in the city at 4 p.m., and I had some radio stuff and TV stuff then. However, the fault was first located at Highfield Road. Most of you, or some of you, have been there. You could see why that was so bloody obvious. I mean, roads don't generally look like that. I want to just highlight some of the things that we saw, that we observed. One was, this is the Hororata River, and this is the fault line going through here. This side of the crust had actually dropped down away from the Hororata, and as a function of that, the Hororata River had diverted. The whole path of the river had changed. So you can see it had once been confined to this channel. This area all through here has moved down, and the river began to flow in a different path. Obviously a major challenge for the landowners in that particular area to deal with. This sort of stuff gets me incredibly excited. I don't know about you guys, but when I see this, this is just amazing. So this side of the fault has moved this way relative to this side. There are all sorts of fracture patterns we see through there that are all consistent with that sort of motion. You can see offset irrigation channels, things like that. The farmers and the people of Canterbury had done an incredible job of having all these linear markers, perfectly straight markers everywhere. Immaculately straight, not even a centimeter out of place. And so we could go and using what we call real-time kinematic GPS units, we could survey these things in with centimeter scale accuracy and determine the amount of offset we had had along the fault. This is important because it tells us about the rupture process. It tells us whether the earthquake energy is consistent with what we see on the ground or whether there are other faults that ruptured, etc., etc. Important stuff to do. Lines of pine trees that had been completely offset. There's the fault going straight through there. Roots that have been broken in half. These lines were straight beforehand, and clearly they are no longer. One of the really interesting stories was in the first flights over, scientists noticed this big curve in the road here, or in the train tracks, as a function of the shortening related to the fault, in addition to a little bit of right lateral motion there. But the work crews were already onto that. They were already fixing that because obviously trains don't tend to enjoy these sort of curves very well. And so they'd fix them. And then they buckled again. Because of course we had the main earthquake, but then there were all these aftershocks where the fault was still creeping in that area, and perhaps still is. Still creeping little bits as it's sort of relaxing after this big earthquake. And so those are the sort of things we observed. But this is something we're really proud about. You might say, oh, it's a line on a map, big deal. But this means so much more. This is several weeks of collaborative and incredibly hard research going in and documenting these things in centimeter scale accuracy along the whole fault, getting a really good idea of the rupture patterns, and that's going to be the sort of food for future research for decades and decades to come. And that's a great collaborative effort. This just shows the amount of displacement. Of course, you can go on the tips of the faults. The displacement is very minimal. You go into the middle of the fault, you get these big displacements. The main thing you want to take out of this is that in places in the central part of the fault, we actually had up to 5 meters of displacement during this event. So the crust actually lurched 5 meters in one earthquake, which is quite an amazing amount of energy. I mean, you know what you felt. Well, that's what you felt in places. That sort of energy. That requires a lot of energy. Now, there's an amazing amount of data that has been collected both during the field investigations and afterwards. And this is just one of these pieces of data that are just incredibly powerful. This is what we call INSAR, and basically this is data collected from a satellite. The satellite goes in orbit and is sending down radar to the ground surface. Now, if it goes around this area once, prior to the earthquake, and then goes around again after the earthquake, the radar signal that comes back is out of whack. It's out of phase. Some of it actually might be a little bit longer, and some of it might be a little bit shorter. And so what this is actually showing is that the satellite was flying along this way. This is courtesy of a colleague of mine. Satellite flying along this way and looking off this direction towards the fault. And what they noticed is that everything here, the ground surface, not just the fault itself, but the land all to the north of the fault, actually moved 1 meter to 1.5 meters to the east, relative to where it was the last time the satellite had gone by. And this area, all through here, had moved up to 2 meters towards the satellite, to the west. Now, that's a mixture of side to side and also probably some up and down. But just imagine the power of that, to have this satellited space telling us, oh, you had 20 centimeters of movement over here, and you had 50 centimeters of movement over here. I mean, it's the sort of stuff you don't actually even recognize all that well on the ground. Pay particular attention to this, because this is quite interesting. We're going to revisit this. This I still don't know what's going on. It's a really interesting thing. But you can see this area has moved to the right. This has moved towards the satellite, and that's exactly what we saw on the ground as well, except that the deformation zone is much broader. Now, there's also incredible data collected from airplanes, which flew over top of the fault scarp and did what we call laser scanning. This is airborne LiDAR. So a bunch of lasers go down from the airplane and come back up, and they give us some idea. They allow us to produce a digital elevation model in incredible resolution for the fault plane itself. Look at this beautiful deformation you can see on the ground surface. This is the sort of things we collected. So this again tells us about the rupture process and the sort of deformation that occurred. What we really want to know, what we all want to know here, what happened? Was this a really big fault and we just had a segment rupture and the fault continues straight into Christchurch? Or was this a full fault rupture? And there's no simple answer to that. It is something that we need to work on. It's something that we need to invest in, and this is a major mission for us all. We need to know whether such structures exist, and we have the technology to tell you, to be able to do this sort of thing. We need to invest money into this. But my suspicion at this stage is that we had an earthquake which was somewhat complex. The seismologists tell us that it involved rupture on a buried, blind structure that we can't really see so much on the ground. We all know that it involved rupture on the Greendale Fault, but it also involved rupture on this blind thrust fault out to the west, which you could see on that INSAR image. It also apparently had some deformation down in this area. We went down and we saw some deformation there that arose from that main earthquake. So it's not just a straight line or a plane on the map. It's a series of faults which actually ruptured during this big earthquake. And it's a really interesting pattern. I guess my take on it is that this side here moved to the east, this side moved to the west. Possibly by moving to the west, you had some thrusting there because you had a bit of a car crash in that area. But also, as a function of this area being pulled away, that's why you're getting this sort of extension going on in this area. And this is our main aftershock zone. All right, so for those of you who live out Rollston Way or live in Taitapu, or one of these areas, there's a lot of aftershocks there that are recording part of this process. And of course, we already talked about some of these strike-slip aftershocks in this area. If you just take some faults with multiple earthquakes, and plot the length of those against the Greendale Fault, it actually maps up pretty well. So one could very preliminarily hope that this was a full fault rupture, which is what I think it is, but this is a hypothesis. I think it's a full fault rupture, and I think that that's in some ways perhaps good news. However, we don't know. Okay, there's a variety of other projects going on. We're investigating what happened to the trees, what happened to water tables, what happened to river systems, what was the pattern of deformation away from the fault, what are the origin of these strange cracks, and all these projects are ongoing. I'm going to close with a few comments on the Alpine Fault because you won't believe the number of emails I got from people in the UK saying we were going to come to Christchurch, but we're worried that the Alpine Fault is going to rupture, so we're going to change our plans. We could have told you the Alpine Fault was going to rupture before the Greendale Fault. I mean, we've all known that, right? And I want to present you with some data, and you can make your own decisions about this. What do we know about the Alpine Fault? Here it is. It's beautiful. We got the Australian plate over here, and we got what I call the Kiwi plate here. It's actually part of this diffuse plate boundary mix. I don't mean to insult you by saying you're a nice mixture of Aussie and Pacific. But basically the Pacific plate is down here, and there's a deformation zone in between, which is this sort of mixture between the two plates. Now, the Greendale Fault is part of this mixture, but the Alpine Fault is the most important part of that mixture, undoubtedly. It is a mature fault, which means it's had lots of earthquakes on it. It's right lateral, just like the Greendale. It's a strike-slip fault. It's got a slip rate of 27 millimeters per year, very approximate, and it takes up 70-75% of the total motion between the Pacific plate way down here and the Australian plate. Okay? We know that it is capable of producing very big earthquakes because it is a long fault. And most of you should, I hope, know by now that the magnitude of the earthquake scales with the amount of area that can rupture in the fault. So the longer the fault, the bigger the potential energy, and therefore the bigger the potential earthquake. It is a locked fault, which means it's not creeping on a daily basis. It's stuck. Things are moving around it, but it is stuck, which means it's storing up this elastic strain energy, which will eventually be released in a big earthquake. I like to say that it's pregnant. It's pregnant for an earthquake. It will have more big earthquakes, and it does present a considerable hazard to South Island communities. Now, all of this is known long, long before I mean, this was known in the 60s and the 70s, so we're very well aware of our alpine fault. Some key points. So this is a map of the South Island. We've got the Greendale Fault here. I drew that little thing on there. And you got the Marlborough Fault system, then you got the Alpine Fault going all the way down the west coast here. All right? Now the timing of these last earthquakes is shown here. 1717, 1620, 1430. This is based primarily on dating surfaces that are inferred to have formed as a consequence of earthquakes, and also looking at changes in growth ring patterns and things like that, using trees, using forests. Primarily, that's one of the main data sets that have been used here. So if we think that during a big earthquake we're going to get a whole bunch of sediment washed out, well, there's not going to be any trees on that surface. And then the trees are going to begin to grow. And so if we can date the trees, we get some idea about the age of the surface, that we can infer the age of the earthquake. Now, there are problems with that, but the data seems to hold up very well when compared to a variety of other proxies. What do we know? There's a larger recurrence interval of major earthquakes, but they're on the order of 100 to 300 years. Okay, that's not very predictable. I mean, it was sort of, there's quite a bit of variability there. It appears that sometimes a segment ruptures and sometimes a very long part of the fault ruptures. So if we have a segment rupture, if we had a magnitude 7 earthquake on the Alpine Fault, the effects in Christchurch would be significantly less than a magnitude 7 in our backyard. Okay? The ground shaking, all the rest. But it is capable, if it ruptures in one go, it is capable of producing magnitude 8 earthquakes. We know that. There have been several major South Island earthquakes, including the 2009 7.8 Dusky Sound. We don't really care so much about that one now, do we? We've got the Greendale to work on. But that was a very important event. The 1929 Murchison, the Arthur's Pass, the Inangahua, all these big earthquakes, as big as the one we had in Greendale, and bigger. And they did not trigger an Alpine Fault earthquake in the days that followed. They were closer, in some places part of that same plate boundary. And modelers would suggest there's probably going to be a slight increase in the stress state on the Alpine Fault from these big earthquakes quite close to the Alpine Fault. Yet there wasn't. And that doesn't mean that there's not going to be an Alpine Fault earthquake from this earthquake, but the actual cause of an Alpine Fault earthquake, in my opinion, would have nothing to do with this particular Greendale earthquake that we just had. The effects would be very, very small. And I just don't think there's any evidence to suggest that we could trigger an Alpine Fault earthquake from an earthquake like we had in the Greendale. Okay? And so I think there's a variety of good bits there. We still are looking at this probability in the range of 15 to 30% of an Alpine Fault earthquake in 50 years. In my opinion, that shouldn't change from pre-Greendale Fault. Okay? So hopefully that alleviates some fears, or maybe not. Don't know. Okay, just to conclude, we had a major earthquake. You've all come to my lecture. Thank you very much. A lot of people missed out. You're now in the position for knowledge transfer. This is going to be online, but a lot of people won't watch it online. And hopefully you've picked up a few things of interest that you can tell your children or your parents or your mates or whatever regarding this earthquake. It's been a great opportunity for Canterbury students. It's been a great opportunity for me personally. It's come at a personal cost, but I think it's in a lot of ways a really fantastic opportunity to learn more about the world that we live on. I think it's also an opportunity to build tighter communities. And I had a go with one of these hoes, these mechanical hoes on the weekend, because I'm trying to mix the sand back into the ground. And these things are really fun and a great way to get out some of that post-earthquake stress. You know, you just take this thing out, but you have to be careful with them because you kind of have to be quite coordinated to make sure they don't run away from you a bit. So that's EQC damage. I want to thank several people. Kevin Furlong from Penn State has been fantastic through the whole process. The GNS earthquake team has been amazing. There's been a lot of commitment from students across all disciplines. It's been a fantastic effort. Tom and the liquefaction team did some incredible work. UC staff and students throughout, I've been very well supported by the university, by my colleagues, and I really appreciate that. And Candace as well. Thank you. Thank you very much. Yeah, sure. I always get a bit emotional at the acknowledgements, you know.
Well, there's a lot to be grateful for. Having a lecturer with those abilities here on campus has been a real privilege, and thank you on behalf of the university for the work you and your team have done. So we do have a few minutes, and we'd like to give you an opportunity to ask some questions. Because we have an audience next door, I will, if I can summarise the question, repeat that using the mic so that we can get that feed through next door. So if there are some questions, please put up your hand and we'll get started. Sir, over here.
What would be the worst possible earthquake we could get on the Alpine Fault? What would be the maximum possible shaking we'd get in Christchurch?
Yeah, a challenging question. So the length of the maximum length of the Alpine Fault. Repeat the question. Okay, so the question was, what would be the maximum magnitude of earthquake that we could get on the Alpine Fault, and what would be the potential shaking that we could get in Christchurch from that event? Okay, I'll do my best to answer that particular question. The magnitude potential that we have of fault obviously scales with the length, and so the length of the Alpine Fault is 400 kilometers or so. If we got an event where we had the whole thing rupture in one go, our estimates are that that could produce a magnitude 8 event. Okay? A magnitude 8 event has amplitudes of seismic waves coming off of the fault 10 times as big as a magnitude 7. And it delivers energy from the fault zone 30 times. 30 times as much energy comes out of the fault. The Greendale Fault might have been 40 or 50 k's long. We're talking about something that's 400 k's long. However, seismic waves attenuate with distance quite a bit. The whole notion of seismic waves reverberating around in the basin, one of the things we learned from the Greendale was that the seismic waves actually attenuated, lost their amplitude and their energy quite rapidly from the earthquake. And so we actually would have expected a little bit more shaking than we got. So if the same thing applies for the Alpine Fault, potentially we could have a similar sort of shaking from a magnitude 8 that we got from the 7. It's difficult to put concrete numbers on these because there's so many variables. There's the geology, there's the rupture process. We could have similar amounts of shaking, but like I showed you with the shaker table, the frequency content would be different. Different buildings would be affected in different ways, and the duration of the shaking would certainly be longer. And so I can't give you numbers. I can't say it would be 0.5 G or anything like that, because it depends on a lot of variables. But that is certainly, I wouldn't expect anything terribly more in terms of the actual felt intensities, and possibly less. But don't hold me to that if it happens. Yep.
How deep is the Greendale Fault, and how does that compare with the thickness of the crust?
Yeah, so the rupture area, the epicentral depth was at 10 kilometers, okay? And that's going to be plus or minus a bit. So let's say 10 plus or minus 1K, all right? And the best that we can see on the surface is like 30 Ks or so. So that's 300 square kilometers. But not all faults rupture in the surface. And so when we're looking at what's on the surface, we might actually only be getting a segment. Sorry, I forgot to repeat the question, but maybe they'll work it out from the answer. So you map something on the surface, but of course there could be lots of fault displacement at depth. And so we think that the fault might be 10 kilometers or 15 kilometers longer at depth than it is actually at the surface. So, but in general, that's the kind of configuration that we think. 10K depth, we know it ruptured to the surface, so 10K by 40K or so, or possibly longer. So 400 to 500 kilometers squared. What was the second part of that? It was,
How big is the crust?
oh,
All the seismogenic layer.
Excuse me, but you were going to repeat the question.
yeah, no, that's not his fault. I just jumped into the answer. The question was, how deep is the Greendale Fault? How big was the area that ruptured? And how does that compare to the thickness of the crust? So where it actually initiated is probably quite close to where we would say the brittle ductile transition is. So where the crust begins to behave a little bit more fluid versus where it behaves really brittly. Given geothermal gradients and those sorts of things, the Earth gets hotter as you go down. The actual thickness of the crust, I'm not entirely sure. My guess is 50 Ks in terms of the thickness of the crust there. I should know that, but that's one of those things that I haven't looked at briefly. You can ask Yarg about that one. Yes?
I'm a geologist, and I had them prepared like a week after
Bugger.
My question is, I read in the paper that people think that this fault, the Greenland fault, could be a reactivated very old fault. But I feel that it's just as well possible that we are dealing with a totally new fracture. And I think it's related to the fact that if you take the Pacific plate moving against its neighboring plate, it has what we call a polar rotation. I understand that the whole system is all being southward.
Yep.
So I have the feeling that this strain of faults like the whole focus might eventually be more to the south.
Yep. Okay, so the question is basically, is the Greendale Fault an inherited fault or is it a new fault? And what may it potentially relate to the southward propagation of the Marlborough Fault system, these big strike-slip faults in the north, further south? The Greendale Fault is a newly discovered fault. We didn't know about it before, but there is some evidence, very scant evidence in seismic profiles that's almost uninterpretable that there might be something there. Of course, from the seismic, it's quite poor quality, and so they drew all sorts of faults through there. But it's possible it's there. I think the main evidence for it being a reactivated fault is twofold. First off, these east-west striking faults of similar sort of length are present throughout the Chatham Rise to the east of us. There are lots and lots of these things, hundreds and hundreds of them. They relate to the extension of the Zealandia continent way back in the Cretaceous. And so we're talking about, 100 million to 50 million years ago, these things were formed during extension. So we know that they're present everywhere. We know they're east-west striking faults in areas where they haven't really even begun to be part of the modern plate boundary, but we can see little bits of deformation picking up on them outside of that particular area. So there's certainly lots of faults that fit the bill for this being an inherited structure. We will learn more about that when we do proper seismic, because we'll see other bits of offset in the fault that maybe relates to previous earthquakes and things like that. The second point I'd like to make is that the world is riddled with faults. There are faults everywhere. There's very little crust that doesn't have faults in it. And so when a big rupture occurs, given the choice, just like water, nature is lazy. It's not going to form a completely new fault when it could use a pre-existing fault 5, 10, 15, 20 Ks away. So just think of the crust as a whole series of, a whole network of faults that some of them switch on during some phases and others switch off and then switch on and switch off and all this sort of thing. So I think, you can pursue your hypothesis, but I think there's a lot of evidence to suggest that it's an inherited structure. Absolutely there are, yep. My colleague Yarg and his research group have been pushing hard for these sort of things for many, many years. And I think like a lot of things in New Zealand, perhaps the money isn't necessarily there. But, there there are new seismic surveys done on some of these structures that I talk about that may have slipped a little bit during the main earthquake. There are papers being published, there's heaps of work that has been done, but this was in an area, a bit of a seismic black hole that hadn't been studied very well. And so we need to invest in this. We need to do lots of seismic, and we need to do lots of geophysics in general to understand what's going on beneath our feet so we can make better assessments of the probability of big earthquakes. And that answer was to the question, are there plans to do more seismic surveys underneath the Canterbury Plains?
Okay, now we're going to have one here and another one over there. So, Robert.
Canterbury Plains have these aquifers all underneath, and the Fonterra depends on them, what gets out, and our drinking water depends on them. Are they changing? Have they changed a lot, and is it going to cost a fortune for the farmers to the dairy?
Yeah, it's a tricky question. It's not a part of the research that I'm personally that involved in, but I will tell you a few things. There was, like I said, the sponge got squeezed during the earthquake. There was flooding. Some farmers told me their paddocks had never been wetter, even after big floods, than they were after this earthquake. And as you can recall, the next day was a beautiful day. There's tons of standing water everywhere. There were changes in water table, big changes in water tables throughout the areas. Some dropped and some rose. My understanding is that a lot of those have actually started to go back to normal, which is what we'd expect from big earthquakes in California, where we see these sort of patterns in the past. Things tend to re-equilibrate because we're sitting on gravels that have a high degree of porosity and permeability, so things can sort of settle back out again. I've done it again, haven't I? Doesn't matter. You got to get here early, right? If you want to. So if the rocks are porous and permeable, then when you have a big earthquake, you can settle things back out eventually, as long as there's no real permanent changes to the sponge. So as long as the sponge still has the same sort of geometry and shape and everything, the holes, then things should return. But the timetable, of course, is definitely out of my realm. The question was, what happened to my water tables? Okay. Yes.
Got a city covered in houses,
Yep.
and some are affected really badly, and some, fortunately for me, not affected at all.
Yep.
We've talked about, or people talk about quality of the soil that we're on.
Yep.
You've talked about wave patterns and frequencies and so on, but many of the houses are pretty much the same structure, but some are very badly affected and some are not. Can you shed any light on that?
Yep. So the question was, I've finally learned. The question was, why was the degree of damage in houses so variable? Even within the same suburb, one person's house is a write-off, someone else's house is fine. I mean, we've had a lot of first-hand experience with that, obviously, in our own suburb. And interestingly, a lot of the new houses on concrete slabs were write-offs, and the 1910 houses that are wooden houses are pretty okay. In terms of the ground condition, I mean, we live on an alluvial plain. This is a whole series of braided streams have worked their way across this landscape for thousands and thousands of years. They've deposited gravels, they've deposited silts, and what's beneath our feet is very heterogeneous. I could dig a hole in my backyard and then go dig a hole in my neighbor's backyard, and the stuff that comes up could be quite different. He might be in an area where he's on the main river channel where it's pebbly and cobbly and it's a different sort of gravel, whereas I might be on what we call an overbank deposit with silts and fine sands and muds. And all those layers are kind of different through the area. So it's not just a total pancake stratigraphy, there's quite a bit of variability. Now that underlying variability in turn interacts with the types of waves and the earthquake magnitude, the water table at the time of the earthquake. All these sort of variables feed into dictating why was there liquefaction here and not 10 meters over here, these sorts of things. So there are geological explanations for why these sort of things have happened. The question is, if we got another magnitude 7 earthquake in the same distance from Christchurch and everything was the same, will we get the same sort of liquefaction patterns? And I'm sort of doubtful that they would be exactly the same, but we have an analog in that there was some liquefaction in Taitapu and Halswell during the 5. In some places it rejuvenated some of these places again. So in terms of building solutions, your guess at this stage is as good as mine. I'm certainly not an engineer, but I hope that I'm pretty confident, and I hope that the right decisions are going to be made. So. Well, it depends what you want. So we're better off on a hill than on a flat. There was quite a bit of ground acceleration, big shaking up on the hill. And one of the things, we can demonstrate with the model, one of the things that happens during earthquakes is that topography tends to amplify shaking. All right? So if you're on top of the hill versus at the bottom of the hill, you tend to shake a little bit more. However, you're on solid rock. And so while you might get more shaking and your chimneys might fall down, you're actually bolted into more solid rock in that area. So there's these sort of variables to consider. But certainly, you've felt every house you went to, you go to your neighbor's place or you go across town or wherever, every aftershock of similar magnitude felt different. I couldn't calibrate myself. I was at my friend's place in Woolston, and I was totally out of whack. I was like, oh, that was a 5. No, that was a 3.5. Oh, that was a 4. No, that was a 6. That sort of thing. I don't know.
Okay, so just one last question over here.
Did I understand correctly that you said we don't know if this is a segment rupture or a total rupture? And if it turns out to be, for instance, a segment rupture that we have, does that mean that we are potentially up for a big one in some unknown future?
Yeah, so the question was this a segment rupture versus a total fault rupture, and how do we know? I'll tell you, so there's several reasons why I am more confident that the full fault ruptured and that it's not part of a through-going structure which goes straight into Christchurch, because it's very easy for us all to just draw a map and go, oh, look, the Greendale Fault is straight, and it just goes straight into Christchurch. After big strike-slip earthquakes on big faults, when you have segment rupture, you're actually able to see an aftershock pattern on that same fault where the area has sort of been compressed and the stress has been elevated. Okay? So imagine you've got the two faults, you've got a fault going like this, and this block here moves to the right. If that fault continues on straight forever, then where it's moved into, you tend to get a big cluster of aftershocks there, as well as some more aftershocks on that same continuation of the fault. Now, in my opinion, there is absolutely no evidence in the aftershocks for that sort of behavior, except for in sort of a 5 to 10 kilometer distance away from the mapped fault tip. And we know that that part of the fault is there in the subsurface and still moving because we can see it in the train tracks, we can see it in the ground. So we know that it extends a little bit further there, but there's nothing in the aftershock patterns to suggest that it continues. The other thing is like I said, when you look at the fault lengths, this particular fault matches up fairly well with other faults, strike-slip faults, which have had multiple earthquakes in terms of its length. So there's no reason to say that it's 30 or 40 kilometers longer. Okay? So there's the aftershock distribution and the argument with other things. I could be wrong, and we need to do seismic to understand that. But even if I look at the aftershocks that occurred in Christchurch on sort of a continuation, and there haven't been very many, on sort of a continuation with that fault, they're an entirely different mechanism. So you can't make a fault plane which goes through and is consistent with that. And of course, you guys all know how to do focal mechanism interpretations now, right? So you could do that.
Well, ladies and gentlemen, I hope you'll join me in thanking Mark for a fantastic lecture. Thank you.